Hey guys, how are y'all doing today? I hope you're doing well. Today we're going to be talking about lesson 7.3, which has to do with logarithms and logarithmic functions. All right. So as we get started on this topic here, I want you to just think about this question for a minute. If I asked you, hey, you have $1, how many times would you have to double that $1 bill before you had $8? Now, I know some of you are already figuring that out in your head, but let's look at an exponential model that would help us to solve this problem. I've got my $1 bill. I'm going to double it. I don't know how many times I'm going to double it. Do I need to double it once? Do I need to double it twice? Do I need to double it 3 times? And so on. And at some point, I want to have $8. So here's my dollar. Here's my doubling. Here's my unknown amount of times, the x, and there's my 8. Okay, so obviously, 1 times the 2 to the power of x, so when we're multiplying by 1, we can simplify that away. And now we just have 2 to the power of x equals 8. And of course, everybody knows 2 cubed, 2 to the power of 3 is 8, 2 times 2 is 4, times 2 is 8. And that's our answer. So I would need to double my $1 3 times. Okay. And I know all of you are thinking, yeah, I already figured that out while you were still talking, Owens. Is this all there is to this? Well, let me change one thing about this question and give you another question. How many times do you have to double your $1 before you have $512? Now, see, it seems, okay, wait a minute. Now I'm going to stop and think about that one. I can't do that just instantly in my head. But the equation we would set up is very similar. The $1, we're doubling it, so times 2. An unknown number of times, we're going to double it. That's the power of x. I want to have $512. Now, how would I solve this? Well, obviously, I still need to just figure out 2 to what power would equal 512. And so then the question becomes, okay, how do I, do that other than going, okay, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. How do I do that? Well, what we want to have a way to find the x. When we have an equation like x plus 3 equals 7, we know that, one of the ways we can go about solving that is that since we're adding 3 to the x, one of the things we can do is we can subtract 3 from both sides of the equation. And because, subtraction is the mathematical operation that will undo addition. So when we want to undo addition, we subtract. If we want to undo multiplication, we divide. What we would like to do here is we want to find a similar operation that undoes the raising a base to an exponent. And so we want to find, that operation that undoes is an inverse operation. So the operation that's the inverse that undoes raising a number to a power, a base to an exponent, is called finding the logarithm. Okay, so that's what this term logarithm, this is where this is coming from. So a logarithm is the exponent, the red one up here, the exponent. A logarithm is the exponent to which a specified base, in our problem it was 2 was the base, in which a specified base is raised to obtain a given value. So there's your textbook definition of what a logarithm is, okay? It is an exponent to which a specified base is raised to obtain a given value. So that sounds, that's certainly a dictionary kind of type definition. It's a mouthful. Let's make it easier. What is a logarithm? A logarithm is an exponent. When you were trying to find a logarithm, you were trying to find that missing unknown exponent. in lessons 7.1 and 7.2, we've been talking about exponential expressions and exponential equations and exponential functions, where the independent variable was the exponent. So what we're going to be doing in these problems is we're going to be trying to find the exponent. And when I want to find an exponent, I'm trying to find a logarithm, because a logarithm is an exponent. I want you to write that down on your notes, put a star by it. It is one of the most important things for you to get comfortable with this concept. Logarithm sounds like a fancy, difficult mathematical concept. Oh, I've got to do logarithms. Oh my gosh. No, you're just finding the exponent. If we were in person and all in class every day and working on stuff and talking about stuff all through class, and I was, instead of teaching you on this video, I was teaching this lesson in class, I would have y'all repeat after me. What is a logarithm? A logarithm is hopefully you just said it in your head, at least you just said exponent. Okay, repeat it several times. A logarithm is an exponent. A logarithm is an exponent. Once you're comfortable with the idea of this new word logarithm, just means, hey, I'm finding the exponent, everything becomes a little bit easier with this process. All right, so in your book here, you have this definition, the definition of logarithm with base b. And so again, this thing's a little bit wordy, and I know that, but we'll just look at it here briefly. Okay, let b and y be positive real numbers, and b cannot equal 1. So it says the logarithm of y with base b is denoted by log, there's the base b of y. So log base b of y equals something. What does it equal? It equals x. Okay, now think about what we just defined logarithms are. Logarithms are exponents. So this thing, this logarithm with a base of b of this number y, log base b of y, equals x. That means what? X has to be an exponent, right? So here it is. Here's that base. And of course, exponential equations have a base and have an exponent. Well, here's that base b right there. There's the exponent right there. And look what it equals. It equals this number right here, this number y. Okay, we're going to talk a little bit more about that in a minute. I'm going to show you, I think, a very clear way to make this connection. But I want to talk about how we say this, because our words are important. How we talk about mathematics is important. It's how we communicate clearly and accurately to other people about the math. So the expression log, and then this little b, and then this y. How do we say this? We say it like this: log base b of y. Okay, log base, and then whatever the base is, that'll be a number a lot of the times, log base 4 of 12, things like that. Okay, so log base b of y is how we're going to pronounce this when we say it. All right, so let me show you another screen here, and I think it'll help clear that core concept up for you. There are two different forms that are equivalent, that are equal to one another, that mean the same thing and use the same values. So every one of them is an exponential equation. I'm going to go back for just a second. This is an exponential equation, right? Because it has an exponent. That's your independent variable. This is a logarithmic equation, or equation. Excuse me. So every exponential equation can be rewritten as a logarithmic equation. And every logarithmic equation can be rewritten as an exponential equation. So we can go back and forth between the two. How do we do that? Actually, it's pretty easy. Whoa. Let's do this. There we go. So you look at this. Here is the exponential form. B to the power of x equals y. That's our exponential form we were just looking at. Here is our log base b of y is equal to x. That's our logarithmic form. And as I pointed out a minute ago, the base here and the base here, you'll notice those are the same green letter. The x here and the x here, you'll notice they're the same red letter. The y here and the y here, you'll notice they're the same blue letter. They are literally the same value. So the x in the exponential form is the x in the log form. The y in the exponential form is the y in the log form. And the b in the exponential form is the b in the log form. So the base here is still the base here. The exponent, remember, logarithms are is a form of the word, the verb is, and is in mathematics always means equal. Logarithms are exponents. A logarithm is an exponent. This is the exponent. The logarithm is equals the exponent. And then the y here, the value that I get when I raise the base to the exponent, is the same value that's going to go right here in log base b of y. So you should be able to take any exponential equation and rewrite it as a logarithmic equation. Okay, we're going to expect you to be able to do that. And then you should be able to take any logarithmic equation and rewrite it as an exponential equation. Because I guess I really should have put arrows on both ends of these. These go both directions. So you can start with an exponential form and rewrite it as a log form, or you can start with a log form and rewrite it as an exponential form. Okay. One thing to remember that your base, there was a restriction on this. The base has to be greater than 0, which means a positive number. Any positive number, just greater than 0, 0.0001 is greater than 0, and it cannot equal 1. Okay, so those are the two limitations here. I talked about the reading, how we read these. I'm going to emphasize it to you one more time because this is always a sticking point every year. Some students have trouble with this, so I want to make it really clear to you. Log base b of y is x. The log base b of y is x. That's how this is read. Okay, log, this is a base, that little subscript. B is your base of, we use the word of because it's of times y is x. Okay, notice again, the logarithm is equals the exponent. All right, so if you need to pause, write all that down. This is a really great way to remember so that you can do those conversions. I want to do a couple of examples with you. Examples 1 and 2 in your textbook are going to be very much like these. They're not the same numbers, so I'm not using the same numbers as is in the textbook for example 1 and for example 2, but they're the same kinds of questions. I'm just giving you some different numbers. So you can practice, these here on the video. You can do the ones in your book separately if you want some extra practice on these. So log base 9 of 9 equals 1. How would I write that in the exponential form? We would write it like this. We would do 9 to the power of 1 equals 9. The base becomes the base of the exponential term. Remember, logarithms are exponents, so the 1 is the exponent. And then this 9, the y is what this is equal to. And of course, 9 to the power of 1 is 9. Little rule that you can pick up here, when the base and the y number are the same, when you have log base b of b, it's always going to equal 1. That's a special property that we're going to look at in a few minutes. Okay, y'all do these next few. Log base 2 of 512 equals 9. So that is 2 to the power of 9 equals 512. By the way, that's the answer to the question that we posed at the beginning of the video. How many times would I need to double my $1 bill before I had $512? 9 times. Okay, so probably not as, you might have thought it would need to be more than that, but it's not, just that few times, just 9 times. This one, what's it going to be? 8 to the power of 1/3 is equal to 2. This one, 4 to the power of -2 is equal to 1/16. So remember that a logarithm can be a negative number. Why? Because exponents can be negative. Remember the rules of exponents? You have a negative exponent, means we use the reciprocal of the base. So that 4, we use the reciprocal of 4/1, which becomes 1/4, 1/4. And then we square it. 1/4 squared is 1/16. So it's actually something that we can do in our head there. And then this last one, you'll notice this has a b there. Log base b of 1 equals 0. And you're like, oh, Mr. Owens, you're not telling me what the base is. You're correct, I'm not. Because this is another one of these rules that we're gonna focus on in a minute, just like this one up here. When you have log base b of b, log base 9 of 9, when these two match, log base b of b, it always equals 1. Because what you're saying is this number b to the power of 1 has to equal b. So it's always going to be the exponent of the log, which of course is the exponent. It's always going to be 1. Down here, log base b of 1 is equal to 0. B to the power of 0 to the exponent of 0 always equals 1. So be careful about that one. Sometimes we get confused and we think, oh, b to the power of 0 is 0. It's not. Any number to the power of 0 is equal to 1. Okay? Except for 0. If 0 to the power of 0 would be 0, but anything other than 0 to the power of 0 is 1. All right. Let's do some example, for example 2. Here's some where we're going now from the exponential, and we're going to rewrite it in the log form. So I want you to go ahead and you can pause the video, answer these, and then you can unpause me and I'll give you the answers. Ready? Okay, I'm assuming you've unpaused me now. So I'm going to do log base 3 of 243 is 5. Because remember, the logarithm is the exponent. It equals the exponent. So log base 3 of 243 equals 5. Here's the others real quick. Log base 25 of 5 is 1/2. Log base 10 of 10,000 is 4. Log base 6 of 1/6 equal 1. And log base A of C equals B. So use letters there just to kind of make sure that one, you know which thing goes where. So if I just we throw weird things in there, you still know this goes here, and this goes here, and you know where to put them. Also, so that you see that, an exponent, of course, can be a variable. A logarithm then can be a variable as well. All right. And I'll mention this third one here just briefly. 10 to the power of 4 is 10,000. Of course, this is kind of where our basis of scientific notation comes in, where we do a number between 1 and 10 times 10 to some power, and that 10 to some power is some version of 1, 10, 100,000, 10,000, 100,000, or it can be a small number, a decimal, 1/10, 1 100th, 1 1,000th, 1 10,000th, and so on. So when we're finding logarithms, we're trying to figure out, okay, what power are we raising 10 to get this number here? And we see that come up sometimes. So just kind of point that out to you. All right, a couple of other things about logarithms you need to know. There's a specific type of logarithm called a common log. And a common logarithm are logarithms that have a specific base, and that is base 10. Much like the example I was just talking about with the log base 10 of 10,000. That was a common log because it had a base of 10. So as the name implies, these are very common, in part because of what I was just talking to you about. So mathematicians decided, hey, we use these kind of logs a whole lot, and writing that little subscript 10 every time is kind of a time waste, kind of annoying. So let's make an agreement that we are just going to not write the 10. Mathematicians are very efficient. You know, I've heard some people sometimes call it lazy, and I don't think it's laziness at all. I think it's efficiency. Mathematicians have found ways over the centuries to make their writing of their mathematics, which sometimes, you know, you've seen very complicated mathematics problems before. Sometimes the things we have to write can be fairly complicated. So anytime we can save time, save space, save effort of writing things that maybe are unnecessary, we try to do that. And so common logs are one of the ways we do that. So if there is no base in a logarithm problem, for example, like this, if it just said the log of 5, so you have to be paying attention, especially if you're new to logarithms, because you might think, oh, 5's the base. 5's not the base. There's no base written here. There's no little lowered subscript right there. And anytime that happens, if there is no base written, you can assume that it is base 10 and that it's a common log. So instead of writing log base 10 of 5, we just write the log of 5. So when you see that, you could see how that would begin to save us some time. And if you had to write a lot of common logs, that would be real nice, okay? And then there's another type of log called a natural logarithm. So where common logs have a base of 10, natural logs have a base of e, that number that we learned about, Euler's number that we learned about in the previous lesson in 7.2. So mathematicians had already come up with the whole, hey, let's leave off the 10. So we can just say the log of, you know, a number is log base 10 of the number. And natural logs are also something we use a whole lot. And again, mathematicians were looking for a way to be efficient. So they came up with another abbreviation, and the abbreviation is LN. That's a lowercase l, so LN. You know, in English, we tend to put our adjectives in front of nouns, you know, the tall boy, you know, or the, I don't know, the wet clothes, things like that. We put our adjectives in front of our nouns, natural logarithm. But some of you are, you know, speak other languages. And if you're bilingual, you know, if you've studied a lot of other languages, you know that a lot of languages, we put the adjectives after nouns. So in other languages, we wouldn't say natural logarithm. We would say logarithm natural, where that adjective comes after the word logarithm instead of in front of it. And when you think about that, then LN logarithm natural makes a whole lot of sense as the abbreviation. So hopefully that will help you to remember that. And you can see why would we want to write LN instead of log base E? Well, we've just cut the number of letters that we have to write in half. So we're cutting our time and our effort in half every time we use a natural log. And like I said, common logs, natural logs, those are the two that are used most often. So for example, if I want to take the natural log of 7, you know, I could write log base E of 7. That would be correct. Nothing wrong with that. It's just, look at this. The ln, or the natural log of 7, is so much shorter writing. You know, and so this is the way you will tend to see that written. This is correct. This is certainly much more efficient. Okay. Now, a couple of things I want you to know here, couple of little things about natural logarithms, and we're going to talk more about inverses here in a few minutes. And but just to mention this while we're on this topic. So the natural logarithmic function, the f of x is equal to the natural log of x, which of course is log base e of x. The graph of that is this red thing right here, okay? It is, this equation right here, this function is the inverse of the natural exponential function, i.e. e to the power of x, which is of course our blue graph here. So we talked about equations like these in 7.2. Well, its inverse is the natural log function that we see right here. And inverses, you'll remember, we've talked a little bit about inverses in the past, but inverses reflect across this diagonal line, which is the linear parent function. It's the y equals x line that goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. It goes through those points, and that is the line of reflection. So when we're talking about inverses, we don't reflect across the x-axis. We don't reflect across the y-axis. We reflect across this diagonal, which is the y equals x line. And so these two are inverses of one another. So just a note, and that will come up when you're working with these from time to time. Just so you're aware about the domain and the range of this function, the natural log of x, the domain is always going to be x greater than 0, because obviously as it comes towards the y-axis, which is at x equals 0, that's an asymptote there. The red curve never actually gets to 0. It never actually touches the y-axis. So it gets really close here to 0 at the y-axis, but it never actually touches it. So x greater than 0. And then the range is all real numbers, because of course we're going down this way, and this will continue to rise. It's rising obviously at a much slower rate than this end, but it is going to continue to go up and up. There's no asymptote on this end. So your range is all real numbers of the natural log function. So good to know. You might want to make a note of that in your notes. A couple of things about using the calculator. As I told you, common logs are very, very commonly used, hence the name common log. And most scientific and graphing calculators are going to have a log button, a log key on them. And so when you see that, those are common logs. Those are base 10 logs, okay? And you'll notice that on most of those kind of calculators, if you hit the second key and then the log button, you know, you're activating the things that are printed above the actual button, and you'll notice it's 10 to the power of x, which is the inverse of the logarithm. So those are a couple of keys that may be useful to you, or really the same key, and then combined with the second. You'll also notice that, for example, on our graphing calculators, we have an LN button. We have a natural log button. So we have both a log button and a natural log button. And that natural log button, there's, we talked about E the other day. Again, it's programmed as it's a log base E. So it's used so often that even though we have a log button for base 10, we also have a log button for base E. Now in our graphing calculators, you can go into the mathematics menu and you can do logs with any bases that you need. But these are certainly the two that are the most commonly used. And you can practice this. Example 4 in your textbook gives you some of these. I'm not going to do that because I think you can push buttons without needing a whole lot of instruction on that. Okay. All right. A few properties, and these are laid out a little bit different than they are in your book, but they're the exact same properties. I just think this is a little bit easier to read. And I mentioned both of these to you earlier when we were doing the examples. So log base b of b is always equal to 1 when the base and this number here, when these two numbers are the same. Log base 7 of 7, log base 12 of 12, log base 2 of 2, all of them equal 1, okay? So anytime these two match, or you can manipulate the equation mathematically to make them match, makes your life a little bit easier. And then here, log base b of 1, always going to equal 0. So these are special properties of logarithms. They're the simple, basic, easy properties, but good to know. These two, the inverse properties of logarithms and the inverse properties of exponents, you need to know these. You're going to use these to help you solve problems. On the homework, on the test, these are things you have to know. So definitely write these two down, put stars by them. You're going to need these. So log base b of b, that's that part. I'm going to go back for just a second. Log base b of b we know is equal to 1. Well, log base b of b to the power of x, all of that then just equals whatever the x is. So log base 10 of 10 to the power of 7, all that just equals 7. So that's good to know. Again, this is one of those things where we may end up needing to manipulate this number and its exponent to make these two match as a way to simplify or solve out the problem. And then this second property, the inverse property of exponents, b to the power of. Now, all this part up here, this log base b of x, this is all in the exponent area. This is all an exponent. B to the power of log base b of x is equal to x. Now, what's the key? Just like here, the b's had to match, the base and this number had to match. Here, this base and then the base of the log and the exponent have to be the same. So if these two things match, this whole thing equals whatever the x value there is. So 10 to the power of log base 10 of 2, all of that equals 2. Keep in mind that if I put this question on a test, it would just say 10 to the power of the log of 2. I wouldn't put the 10 there because it's a common log, and I would use that advantage of not having to write the 10. But that can be a little tricky because now, when you see it like this, you say, oh, those two match, and it's real easy to remember that. If the 10's not there, you might forget, oh, there's a little 10 right there. There's a base there for that logarithm. These two are the same. So I know this equals 2. So remember that, because that does come up from time to time, whether it be a common log or if it was a natural log. If this was e to the power of the ln, the natural log of 2, then that would still be e to a log base e, even though that ln doesn't have an e in it anywhere. But we know it's there. It's an understood thing. So we have to be paying attention to it. All right. Let's do a few examples here. Here's example 5 from our book, and ask us to use those inverse properties. And they give us two different expressions that we're going to work with. So 10 to the power of the log of 4, and then log base 5 of 25 to the power of x. So let's do the first one. So 10 to the power of the log of 4. Well, how much does it equal? It equals 4. Why? Because as I just got through talking about, this is a common log, right? This is a log of base 10. So 10 to the power of log base 10 of 4, 10 and 10, they match, they're the same. So the property tells us it's just equal to this number, which is 4. So that one's pretty simple. Now, let's look at this next one, okay? Log base 5 of 25 to the power of x. Now, this one doesn't follow the property where the base and the 25, are the same. They're not the same. But your math brain ought to be going off that, hey, 25, that's like a multiple of 5. And I know that 5 squared is 25. Hopefully those kinds of things are happening in your brain. You're making those connections. And so we see if I rewrite 25 with something that it's totally equal to, which is 5 squared. Well, now look at this. Now log base 5 of 5, these two are matching, but now I have two exponents. But remember the properties of exponents. When you have an exponent raised to a power raised to a power, we use the power of a power property, and we do 2 times x, so that becomes just 2x. So now I have log base 5 of 5 to an exponent. The exponent is 2x. So what does that whole thing equal? 2x. All right. So that's how we use those inverse properties to simplify an expression, get it down to something that now is 2x, would be easy to work with in context of a larger problem or a larger equation that we're working with. All right. Let's look at example 6 out of your textbook here. And again, a couple of different examples. So here we're asked to find the inverse of the function. Find the inverse of the function. So let's start with this first example, example A. So remember that we know the inverse. Remember I talked to you about this with those graphs a few minutes ago. The inverse of f of x is equal to 6 to the power of x. The inverse of that is log base 6 of x. So I notice I use the inverse notation, f inverse of x. So this is my function, f of x. This is the inverse of f of x, f inverse of x. So 6 to the power of x, its inverse is log base 6 of x. Now let's try it with this natural log here. So we have our natural log. I'm going to change the function notation f of x to y. And now I'm going to do the inverse. Remember, for inverses, we can switch the x and the y. So I switched the x and the y here. The y became an x. The x became a y. And now I'm going to set out to solve this. So I'm going to rewrite this natural log. It's still a logarithm. So I'm going to rewrite it. Remember, it's just log base e, right? That's what ln, natural log, means. It means log base e. So I'm going to rewrite this in exponential form. So the base is e, the exponent is the x, and this is what it's equal to. So e to the power of x is equal to y plus 3. Okay. I want to isolate the y here. So I'm going to, right now, 3 is being added to y. So I subtract my 3 from both sides of the equation. And now I get e to the power of x minus 3 is equal to y. So guess what? I have written the inverse. So take my equation, change the y over to the inverse function notation, f inverse of x. Using that for my original, its inverse is e to the power of x minus 3. All right. Okay, so last thing I want to talk to you about here is using the inverse relationship between exponential and logarithmic functions in order to graph the log functions. So you'll see this core concept in your book. So here we have the graph of f of x is equal to log base b of x. Now this is the graph when b is greater than 1. Okay, so when b is greater than 1, we're going to have a graph for log base b of x that looks like this. And then its inverse, which again reflects over that y equals x line, the inverse then is right here, log base b of x. Now, on the other side, what happens if b is not greater than 1? Remember that b has to be a positive number and it can't equal 1. So the options are either it's bigger than 1 or it's between 0 and 1. Well, what happens when it is between 0 and 1? Well, when it's between 0 and 1, then we get this graph right here, the one in red, the log base b of x. Okay, and then we see its reflection across the y equals x line in blue right here. And you can see this portion's reflected up here, and this portion is reflected down here. So even though it crosses the line of reflection, that's okay. Crosses the line of reflection here, but it's still a reflection. Okay, so it's still the inverse of those. So got the log base b of x, and I've got the b to the power of x. And here I've got my log base b of x and my b to the power of x. What's the difference? This one is when b is greater than 1. This one is when b is between 0 and 1. So using that knowledge, let's look at this last example. Graph f of x is equal to the log base 2 of x, and identify the domain and the range. So first thing we're going to do is we're going to find that inverse. So we just went over how to do that. So I'm not going to do that right here, but we just went over just a few minutes ago how to find that inverse. So our original function is log base 2 of x. And so its inverse, we would rewrite it y equals, switch the x and the y and solve it for y. The inverse is 2 to the power of x. So there is my inverse for that function. Okay. Next, I'm going to make a table of values for the inverse, because 2 to the power of x, I can do those calculations, and I'm going to make a table. Remember how we make a table? We pick x's that we want to use, and then the equation gives us the corresponding y's. So I plug in some values for x, some basic values like -2, -1, 0, 1, 2. I plug those in up here, and I get my output. 2 to the power of -2 is a 1/4. 2 to the power of -1 is a half. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4, and so on. So I get some of those, and now I'm going to graph them. Okay, so I might not have known what log base 2 of -2 or log base 2 of -1 or log base 2 of 0 or log base 2 of 1. I might not have known what those are, but I can do these calculations. So that's why we got our inverse and we did the calculations there. Now I can plot them on a graph. So I'm going to plot those on the graph. Now they're the ones that are here in blue. Okay, so I'm going to plot these points. You see me at -2 and then up 1/4 right there. And then at -1, 1/2. So I go over here to -1 and go up a half. Then at 0, 1. So I'm at 0 and I go up to 1. Then 1, 2. So I go over to 1 and up 2. And then 2, 4. So I go over to 2 and up 4. So I have all these points, and now I can connect them into a smooth curve. And I've got my graph of the inverse function. Now remember that we're going to reflect across this line, and the reflection is going to be the original problem, the log base 2 of x, because these are, this is the inverse of this equation, and we know it's going to reflect across this line. It's really easy once I have a table to graph these points. I obviously can visually reflect them across the line, and you see they all reflect across that y equals x diagonal line. But you can also just take the ordered pairs and flip the x and the y. So this becomes the x coordinate, that becomes the y coordinate of this other problem. So I go over 1/4 and I go down to -2. I go over to 1/2 and then I go down to -1. I go over to 1 and I go to 0. Don't have to move. I go over to 2 and I go up to 1. I go over to 4 and I go up to 2. And those are the corresponding reflected points for the original problem that we were asked to graph. And then of course, identify the domain and range. We talked about this earlier. We're coming up here to this asymptote at the y-axis. We're not ever going to touch the y-axis, so we're never going to quite get to 0. So our domain is greater than or equal to 0, but our range is all real numbers. All right. Okay, folks, that wraps it up. Hope you have a great day, and we will talk to you soon. Goodbye.